Green's theorem, part one. This is a basic statement of Green's theorem over here. We have a path, a closed path, traversed in the counterclockwise direction. It's a simple closed path. It doesn't cross itself. And it encloses a region R for region. And it turns out we can, and if we have a vector field, mi plus nj, this is strictly a two-dimensional statement. This is a plus here. You can misinterpret it as a times. We can integrate f dot dr. That would give us work going around here counterclockwise and gives us the same answer as if we do this plane integral of partial of n with respect to x minus partial of n with respect to y. And that's an integral over the enclosed region. And so, for instance, if you break this up into a grid, this would be dA, which we can express as dy dx, for instance. Part one, what we're going to do is pick an example, and we're going to pick through evaluating this side. And then part two, we're going to take the same example and evaluate this side. That's usually the easiest part, and show that we get the same answer. So the way we evaluate this gives you a pretty good, strong intuition as to what it is we're evaluating. So we're going to start with the vector field 2xi plus xyj on this Cartesian product 0 to 2 cross 0 to 2. And it gives us this region here. And what we're going to do is break this up into four different segments. C1 along the horizontal, C2, C3, and C4. And we're going to actually do the integral along these four segments and then add it up at the end and see what the answer is. Well, first of all, f dot dr is just simply this dot dxi plus dyj, and it gives us 2x dx plus xy dy. And what we have to do is integrate f dot dr around these four paths, and that's what we're going to do. On C1, I wrote all this out because it's difficult to fit all this on a small board. So on C1, we're talking about right here. dy is 0 because our elevation is staying the same. Y is 0. That's y equals 0. X goes from 0 to 2. And so we can simplify this to put a 0 there and a 0 there. It gives us 2x dx plus x0, 0, 2x dx. And then we can simply integrate 2x dx from 0 to 2. 0 here, 2 here. Gives us x squared from 0 to 2, which is 4. On C2, okay, we already did this here. Now we're doing C2. We're doing that vertical climb. dx is 0 and x is fixed at 2. Y goes from 0 to 2. F dot dr, 2 times 2 times 0 plus 2y dy. We plug into here, of course, and we get 2y dy. Then we integrate 0 to 2, 2y dy, and we get another 4. So far, our integral total is up to 8. On C3, now we're going back this way. This will be important in a minute. Y is fixed at 2, dy is 0 because y is not changing. X goes from 0 to 2. And f dot dr is 2x dx plus x times 2 times 0, 2x dx. Now to integrate, we have to start here and end up here. So pretty important, we're starting at 2 and ending at 0. So we get 2x dx, x squared from 2 to 0. It ends up being 0 minus 4, which is negative 4. Okay, the sign makes a whole difference in the world and the direction. Now we're going to come back down here. On this segment, on C4, x is 0. This is x equals 0 right here, the y-axis. dx is 0, y goes from 0 to 2. Actually, it goes from 2 down to 0. F dot dr is 2 times 0 times 0. X is 0, dx is 0. X is 0. And so we get 0 dy. Well, guess what? We're going to integrate 0 dy from 2 to 0, and it's going to give us 0. Okay, you're adding up nothing and you get nothing. You can put a constant, evaluate a constant from 2 to 0, and you'll still get 0. So the sum total of our integral is 4 plus negative 4 plus 0 adds up to 4. We'll be back for part 2, where we will evaluate this side. I'll get it all set up to expedite the video, and when we integrate that side, we'll get 4, as you may have guessed.